Hi, students. I thought I would work a problem just to show you why why I say the conservation of energy method is so nice. So imagine that I gave you a problem like this on a quiz, exam, homework, whatever, and in the problem, I've got a puck which has been pushed by this spring, and so it has an initial velocity up the slope of 20 meters per second. And let's just suppose the mass is 2 kilograms, although I can tell you that the mass is not going to matter in the long run because it won't, the answer won't depend on the mass. But anyway, let's just say that. And so the question is how far up the hill it's going to go. Now, the old way of doing it that you've learned so far would entail finding the uh, the acceleration, or actually it's slowing down, so the deacceleration of this puck, and then using the big five formulas to figure out how far up it goes. And then to find the acceleration, you would need to find the force in the downhill component, which would then involve trigonometry, the 30 degrees, and all of this. So it's really quite challenging, and I want to show you that conservation of energy is an easier way to do it. So so what I want to do is first of all, I want to start by defining the starting height. So I'm going to make, maybe I'll use a different color here, make a little dashed line here that defines the y equals 0 location. And I drew it going through this little black dot on the puck, although it doesn't really matter what reference point I use. I could use like this corner or something. Um, okay, now, and so what conservation of energy is going to do for us is answer this question. It's going to tell us how high it ends up going. So let's say up here, this is where it finally wound up. Okay, and so what conservation is going to tell us is this height here. So y final equals what? Okay, and here y is equal to 0. So at this location y equals 0, and that's y initial. Okay, so here it's got a total energy E, which is equal to the kinetic energy plus the potential energy. Now, here the potential energy is gravitational potential energy. You could, I mean, there is a spring here, so we could conceivably be talking about spring potential energy, but for now it's gravitational potential energy. Maybe I'll just put a G here to say that. Okay, and according to the law, whatever this number is, it's going to stay the same. Okay, so this quantity E is going to be conserved. It's going to stay the same. All right. And okay, so now we have so let's call the initial total energy E initial, and the final total energy E final. Okay, so let's break this down now. So E initial is equal to K initial and plus the gravitational energy initial, and this it has to equal to K final plus the final gravitational potential energy. Okay, so E initial equals E final becomes E initial equals E final. Okay, so let's keep going with this. So K initial is 1/2 mv initial squared. U initial is mgy initial. K final is 1/2 mv final squared. And U final is mgy y final. Okay. Now, y initial is 0, right? So this is going to be 0. When it gets to the top here, here I might as well write it, v final is equal to 0. All right. So that means, okay, so this is v final equals 0 right here. So this is going to be 0. Okay, so what we have is 1/2 mv initial final equals mgy final, right? We don't need this anymore. We have this equal to that. All right, let's solve for y final. So y final equals 1/2 mvi final initial, squared, right? I just took this and put it here. Here's my y, I put it there. And I'm dividing both sides by mg. So I'm going to divide by mg. Aha, at this point, the m's cancel. All right, so now I can plug in my numbers. I have 1/2. We have v initial, which is 20 meters per second. And then don't forget to square that. And this is divided by 9.8 meters per second squared. And notice that the seconds squared, those units are going to cancel the seconds squared. You're going to have meters squared here, which gets partially canceled by the meters here. And so now we have, let's see, 400 divided by 2 is 200. So 200 divided by 9.8 gives me 20.4 meters. Okay. So that's right there. There you go. This was easier than using the trigonometry to find the net force then to find the acceleration then to use in the big five to see how far up you go, and then more trigonometry to see how far up in the vertical distance that translates to. So I think you will agree with me. This is an easier way of doing certain problems, and certainly for this problem, there's no doubt.